Great. Thank you, everyone, for having me right before lunch. And I'm going to be doing a little bit of maybe just a little pivot compared to some presentations you've heard thus far. I'm going to talk today about the transatlantic infrastructure. So as part of HIBALL and so on, bringing together different work packages, this is the efforts of Work Package 4 to develop that transatlantic infrastructure to help share and process BigBrain datasets. So I'll just give a brief overview to contextualize where things are at and what does it mean by building such a bridge between different, I would say, ecosystems, and what it really means to build an architecture that is really at a global scale, not just looking at across the Atlantic, but beyond. Beyond that, ourselves going forward, I'll talk about the infrastructure that pulls these pieces together and help us then, of course, various scientific endeavors that you've heard thus far, such that it actually then makes it more reproducible for the science that it gets done. It helps it scale up since we're dealing with large volumes of data, but also the diversity of that data. And then it also facilitates the collaboration, such as in the context that we're in here today. And then I'll close with just a couple example workflows that are implemented within this bridged architecture. So if you look at the challenges, there's significant ones. We're all working with large volumes of data, large variety of data, but we're doing it in a context where we're doing it, as a collaboration, and therefore we each come with our own sets of infrastructures and ecosystem tools. But as we've seen from the various presentations as well, the work that is getting done is trying to extrapolate to other endeavors, so that is very much truly interdisciplinary. So to do this, though, you have to say, okay, what does it take? Of course, it does the algorithmics part of it as well, but certainly we need infrastructure, the pipelines that pull things together to actually then accomplish the science. And if you look at, there's a significant number of factors when you're going all the way from data acquisition, collection, management, all the way to the end. But the highlight here that I'm going to try and extract and show you here today are the parts that touch upon building, what does it mean to build interoperability between architectures? What does it mean to deal with different potentially data governance and security requirements? And also then, in the end, manage the orchestration of the workflows such that you can leverage the different infrastructures that we have available for computational resource usage as well as cloud usage. And in the end, making sure that all then integrates and ties it together in a nice big bow so that it can be reproducible. So if you look at the challenges that are there, so of course we have, when things got started, we had infrastructures, and there still are infrastructures on both sides of the Atlantic in the context of the big brain in Canada, and in the Europe side. The fundamental base layer, of course, is the HPC resources. Those are physical infrastructures, but of course, on top of that, we have pieces of the software layer where people then interface to access data. They might then, of course, have to build upon that, any other interfaces that may be specific to their individual needs. So, but of course, this presents potentially some diversity, which is great, right? We want to have an ecosystem, but at the same time, we want to work together in a collaborative fashion, so you need to find ways of building something that fits together and can talk with each other. And in the end, we're not working in isolation. We want something that can be extensible to other domains of activity. But because of the way these pillars of different layers are made, there are some challenges in there. Even though there's fundamental things on how HPC resources are used, there are some barriers, such as, for example, how applications are presented on the individual systems. Those are not uniform between one system to another. And of course, particularly when we're talking about the volumes and volumes of data here, moving data is very, very costly, and even that's in the situation of where data is permitted to be moved. If we're talking about other situations, we're also different depending on the data. There may be certain contexts where that data actually has to stay in place, right? So we have those barriers that we want to deal with. And lastly, again, depending on the nature of the configurations, we have different and non-uniform authentication and user identification systems. And therefore, we still want to make sure that we're compliant with the regulatory needs of those particular institutions that are providing resources, but also the end users that are connecting to them. And of course, looking at this, it presents a gap. We've heard a few times crossing the bridge, crossing the gap. This presents an infrastructure gap that we want to then close. So as part of that, so this represents then the different layers, whether it's the computational pieces, the data, all the way through the pipelines, all the way up through the top. So you would see essentially at the beginning these two different entry points of access. So the idea behind this effort was to then do a transformation of this architecture such that it actually then takes some common pieces and then make them interoperable. And with that, we use CBrain as the foundational layer for that interoperability, while at the same time making sure that we can then conform to individual requirements at the different sites, whether it comes for things like identity management, authentication, authorization. So for example, on the JSC side in Jülich, the service account model was extended to be run also on their framework, such that all the detailed logging of actually who the users are is recorded for real-time access from the JSC side of things. And then on top of that, we built, of course, an extension of the CBrain storage layer that already had tied into things like DataLad on both sides, but then we made that bridge across, and we have a essentially nearly complete now iteration that allows that DataLad connectivity for CBrain to talk to eBrains as well. Building upon that, of course, is then having the inventory of software and scientific tools. Having things in a containerized fashion makes those things reproducible and also portable. So that's the baseline infrastructure that we use within CBrain for the application space. Things are by default containerized. And then by having this infrastructure set up, then people across both sides of the Atlantic can leverage either, of course, if they have their methods that they're doing direct login access, that's fine. But from the CBrain context, then people are able to access through the web portal, leverage the containerized applications, and then run data in place wherever the data itself is located, so that someone across the world, wherever they may be located, can run applications directly on the data in JSC, or correspondingly the same thing on data that might be located in Canada, for example. And that is really the key capability. You bring your compute to the data, not the other way around. So when we look at then the transformation that's been made, when we look at the architecture, even then we had these two separate pillars before, we've made the HPC systems interoperable by having these foundational layers added on. We bring the actual applications and scientific tools to the data itself, and we have this harmonization layer between the authentication and identity management that is occurring, again, through the CBrain interface. So if you look at that, if you haven't been familiar with what CBrain is already or attended the session yesterday that was done for the training workshop, it's a distributed computing platform that was developed out of the lab of Alan Evans at McGill over the last 15 years that deals with multimodal data, but at the same time connects it in a federated data and compute space that makes it easy for people to transition and benefit from going from the command line experience to instead using a web-based UI. Of course, we have detailed APIs underneath that make it easier for more complex workflows. But the idea then is to help facilitate that transformation of work experience such that people can easily scale up the scientific endeavor that they're doing and make sure things are, again, reproducible, while at the same time making sure that you can collaborate with your colleagues. So more details are available on the website. And this just gives you an overall workflow view of what the CBrain system does. It ties together with other systems, such as more on the data collection and management side, also from Alan's lab on the LoRa side, but particularly on the CBrain context, again, the scientific tools, which are all containerized, connect into the data space, and the data space uniquely, though, can be brought from data that is imported directly by the user, or nicely take into account the fact that there are data repositories out there, either standalone or based upon DataLad, so that you don't have to have unnecessary data duplication. We have a common repository for things like the UK Biobank for all the McGill collaborators, but we also draw upon things like OpenNeuro. We also draw upon, of course, things like the other open data sets, including the BigBrain and now the connection to eBrains. So if you look at a typical workflow, one of the real benefits there, if you extend this, is really to make it very simple to have that relationship maintained between one's input data and what we then correspondingly describe using a boutiques JSON file to then map what the scientific tool is doing, which you would normally try and script on a command line. We have this in a JSON formatted file using boutiques to then present the web UI view of the tool, and then that gets run on one of the connected resources across the CBrain with all the results, both either the input or the output directly viewable within the browser. So this just gives a representation of what it looks like within your interactive experience with using CBrain. You see all your data spaces into a single pane of glass view, whether it's across one or multiple systems. You can do them directly within the web browser visualization using our Brain Browser visualization tool. And you can also manage your workflows and your tasks, seeing the status of them, drill down, view the outputs, and again, maintain that relationship of knowing input, data, tool, and output, so that connection is always there. Right now, we have about 160 different tools in the inventory covering the full spectrum of categories. I won't go into those details. You can follow the link there for more information. But again, the key elements being that are containerized using boutiques and then cBrain for the orchestration. These are just some of the example connected to HPC resources around the world. And you know, we have also generic connectors that connect to basic cloud-based resources as well, all the popular ones, as well as any more on-prem ones that people might be operated with over 2,000 users now. So just to finish up with maybe some examples of some of the tools that highlight this global interoperability. For example, if a user anywhere in the world wants to access a data set, for example, it might be in Ulich, for various reasons, it may or may not be, we don't want to move the data, we want to keep it in situ in place and locked in there. If they want to run, for example, HIBALL Unfold from Jordan de Cracker, for example, that tool is already containerized and integrated in cBrain. All the user has to do then, from wherever they are located, they specify the operational parameters of the tool through the web interface, where they wanted to save it to, in this case, selected to my location, which was in Montreal. And then through the interface of cBrain, we're able to see that it was run specifically on the Eureka resource here in Germany, and at the same time, all the fields and output and logging is directly visible to the user in cBrain. So again, we bring the compute to the data. And as a corresponding other one, as a last example, again, another user located anywhere in the world, they found another set of data that's interesting to them that might be located in Canada. This is just an example. Images provided as part of the cell detection tool from Eric Upschulte. Again, the tools, we've heard about what that one does particularly, but in this case, we want to keep the data resident in Canada. Again, cBrain provides the means by which the tool can be brought to the data. All the parameters that are normally done on the command line are executed there and specified. Run, again, on an HP resource in Canada with all of the output then brought back to the end user through cBrain. Oops, I skipped too far ahead. So to wrap up, as you can see, we have big data, big compute that we're working with. I think that's very clear from all the presentations prior. And we also want to make sure that we are able to extend this to other domains of applicability. And this infrastructure, even though it's been done in the context of BigBrain, it's extensible to other domains and other activity areas. It really has addressed the ideas of interoperability. We don't want to recreate from scratch. We want to make sure those elements are in place so that we still conform with the security requirements. And lastly, we've really done a good job doing the harmonization for the authorization. And again, keeping in mind that we transfer the tools to the data. So with that, I'd like to just, keep this in mind that this is obviously serving as a good platform for other endeavors. But with that, I'd like to thank my colleagues on the project and our funding agencies who've graciously supported this effort and where it's going forward. Thank you.